Okay. Well, like I said, our TV is on the fritz, but I mean, don't just judge it from this screen, but maybe when we go into Unity and stuff like that, let me know in the end which is actually better, this screen or the TV for class presentation. Plenty of uses for the TV anyways, but is there an opinion right off the bat? Like, is this better or is the TV better?
It's taller. It's raised higher enough.
So, okay, so it's easier to see this up high. What about the picture quality itself? Huh?
It's way worse.
This is way worse.
Yeah.
Okay, so the TV's better. You would just prefer for either the room to be stadium seated, or or for the to put some sort of ramp in or something like that. Yeah, that stand actually will let the TV go higher, but then it won't clear the doors. Yeah, we have it set right so it's like at the microscopic level it will it will slide underneath the doors in the department. But yeah, so I'll maybe ask again at the end when we start seeing Unity and stuff like that in the. All right, yeah, we're cooking. Okay, so we've been looking at procedural generated things, and as I mentioned last time, the next like several game advancement assignments are up. So you can keep working on those and get them submitted, and I'll grade them. But we're looking at procedural generated stuff in here. Now, let's see, where do we leave this? So I created a couple of. So last time we were kind of talking about the when we deal with scale inside of a parent transform, that the 1 to 1 to 1 scale of something is relative to its parent, not relative to WorldSpace. Right, so that's something to keep in mind as you have children of objects. So this last guy, he has a was it? Which one was it? This one. This one is a scale of 1 to 1 to 1. This guy it looks like that. He is, off kilter. He's not 1 to 1 to 1. But if I add a child to him, another cube, that new cube has a 1 to 1 to 1 scale relative to his parent transform. So it's all askew and stuff as well. So this guy here looks the same as this guy here, but this guy's scale is 1, 1, 1. This guy's scale is 5, 1.61. Make sense? And then if we move this dude outside of that, notice that his scale becomes his parents, what his parents' scale was, as opposed to 1 to 1 to 1 in the rest of the world like this guy. Okay, so at the top level, we have a transform represented by the entire scene. So that's usually called WorldSpace. All right, let's add that to the notes here, because that's something that's used pretty commonly in some of the different functions. It says, like true or false relative to WorldSpace, something like that. So we have this thing called WorldSpace. And we can think of this as the scene. Let's see, let's call it the transform related to the scene. And then furthermore, we can say that all game objects live within this transform. Some game objects may live within other transforms that live within the WorldSpace transform. Make some sense how that stuff works? All right, so that's where it comes down to scaling things relative to other things. That's going to be important for kind of where we're going with this. Now let me see if I talked about, we got that. All right, so did we talk about data representation languages last time? Blank stare, so probably not. Right, all right. I've mentioned it in other classes, so all of you in here have had at least 200, 250, some of you have had 300, that kind of stuff. When I say data representation language, what am I talking about? If you had to give me kind of a high level description of what that is, what might you say? We've definitely seen this phrase, at least in 200 and probably at the review of 200 in the 250 class. So this was this would have fallen underneath the category of what's a programming language versus what's not. So we say that programming languages, 100% of programming languages have facilities for variables, conditionals, and loops and functions, right? Okay, so if something else, and I probably talked about this in the context of when I see like a resume or something like that, and it lists, here's the programming languages I'm familiar with, it's pretty common for people to write down like HTML. Do we know what HTML is? What is that guy? Okay, this is website crap. It's we call this a tag-based language interpreted by a web browser, which turns data into, call it, pretty pictures and text. All right, so we're representing what we want the look and feel of our website to be. So if I go here to like google.com, all right, so we would call this a fairly simple website. I right click on this and I say view page source. We have all of this stuff that pops in here, and this is all of the, let's scroll down to when we actually get to some HTML stuff. Actually, right now this is all JavaScript. Somewhere in here there's going to be a little HTML. Yeah, here we go. Yeah, so here's like a link, a hypertext link in HTML, this type of stuff. If I do a search for, wrong button. There's the title tag right here, and it says Google in it. And notice that the title of that thing is Google. That's where that came from. So, the thing that actually made this tag say Google, my phone, when I said, okay, Google, it started looking for stuff, came from this data representation right here, which is called HTML. Make sense? All right, so HTML stands for hypertext markup language. All right, so we might say that a data representation language, that's kind of my term, in many cases is referred to as a markup language. We almost call that maybe a synonym, something like that. So something to keep an eye on. Okay, so HTML is a tag-based language. So what it means is we have these things like, just close this here. Here's an opening title tag. Here's a closing title tag. And the meat in between is the actual data we're representing. Okay, so when I say tag-based language, HTML-like languages have like the little angle bracket title, angle bracket, name of the tag, close angle bracket, followed by your data, followed by angle bracket / name of the title or name of the tag, close angle bracket. All right, that's the syntax for HTML. Now, from that, we have something else called XML. What's XML? Okay, well, HTML existed for a really long time before XML was even a thing. Okay, but there is a link there, though. So what does XML stand for, first of all? It's Extensible Markup Language. All right, and what does the word extensible mean to you? When something is extensible, can grow, Okay, this is the root word's kind of an extend thing. Okay, so we can grow, we can modify it, something like that. It's malleable. So XML is a language designed to be extended to fit the kind of data you want to represent. Okay, so it's a markup language, which kind of should start screaming data representation to us. It is extensible, which means that we kind of have these core tools and we can use it to represent any sort of data we want to represent. HTML is an example of something that could have been built in XML, even though HTML came out first. So HTML was the influence for XML, even though you can now implement HTML using XML. And that's something called XHTML. Okay. But with XML, we now have the ability to represent any sort of data, not just data related to website stuff. Okay. Where a website has a title, it has a body, it has, header tags, it has, layout stuff for, making things centered or bold and, all sorts of stuff like that. Okay. So those are things that make sense on a website. Well, things that make sense for an application sending information to another application, maybe it doesn't need all these extra special website tags, but it might need like a first name tag and a last name tag and a social security number tag, stuff like that, for marking up data with information that's related to that data. See where the markup stuff comes from? All right, so it gives us the ability to use a tag-based cadence similar to what HTML has already modeled for us in such a way to represent other kinds of data that's not website stuff. So this allows us to represent data in a familiar way. We'll just say HTML, other than website data. All right, so it takes its cues from the tags from HTML and says, hey, what if we wanted to mark up other kinds of things other than things that involve data? So with the case of HTML, our client, our end user for the HTML code is a web browser. So web browsers speak the language of HTML. So if you feed it HTML, it'll interpret that and turn it into pretty pictures and text, right? Now, if we move outside of that and say, okay, well, now we're going to create an XML document that lists all the legal tags. Maybe you're doing patient records between two programs. Okay, so you have patient records. And you're going to say, I'm going to list all the tags that involve this, like I just mentioned, first name, last name, stuff that involve patient record stuff, right? Now, all of a sudden, you have two computer programs, and maybe one of them generates the XML representation of a patient record. Maybe you have a Java object or something like that is a patient record, and then when you can export that to XML, and it creates the crazy string of opening tag, first name, whatever the first name was, close tag, so on and so forth. So it effectively encodes your objects into XML. Then you could transfer that over the internet just as a string, right? Effectively, if we add some additional things in here, I'm going to create this on a separate slide. We have something called Deserialize. And actually in some older languages, this would have been called Marshall. So 1 L or 2 L's or 5 L's? Okay, now we're definitely wrong, so then we'll just go with that. Okay, so it's something called Marshall. If you're marshalling data, but the modern term for it is serialized, so don't worry about the Marshall thing. It's more just older trivia. So to serialize data means to take from an object form into a data representation form. All right, so that's how we serialize data. Similarly, we can deserialize data, and this takes a data representation form and turns it into objects. in a given programming language. So you can now work with them programmatically. That makes sense? So we serialize this stuff to send it over the internet between two programs. The program that catches it is going to receive a string. It's going to deserialize the string and then have a bunch of objects that it can now work with. Make sense? Okay. So that the whole purpose of these data representation languages is to have data shared between programs. All right. Could be any kind of program. So this is our XML. And we can create, I'll just throw that as a thing. So we can create HTML using XML. And this is called XHTML. In most web browsers, I haven't really found actually where it is in Chrome, in the newest version of Chrome, but it's somewhere in there. I haven't spent a large amount of time looking for it. Just at a glance, I couldn't find it. Do you know what? So most web browsers have a toggle somewhere that says whether or not you want to enable XHTML or not. Do you know what that does? If I enable XHTML, what's that going to ultimately do for the browser? And why is it off by default? Well, isn't in theory, isn't XHTML just HTML? I mean, if you saw a correctly written HTML web page, and right next to it you had the same XHTML version of that page, they would look identical. Same thing. Problem is that old web pages, when when kind of the web was very young, we had these tools like Microsoft Front Page that allowed us to generate. You would kind of create your web page like in a Microsoft Word document type thing, and then it would, let you save it as HTML, and it was kind of the Microsoft version of the HTML that wouldn't always have corresponding closing tags to the opening tags. It used a loose version of HTML, and the web browsers. So this kind of started the original web browser wars. If you've ever done anything with web design or talked to a web designer, one thing they have to do commonly is they have to test a page that they create on multiple browsers to make sure it looks right on multiple browsers. Because over time, well, in the early days, those browsers had to have some exceptions put into them to handle poorly written HTML. So you imagine that, like Internet Explorer would have had a whole bunch of exceptions to make sure that it worked for anything that was generated by Microsoft Front Page, right? And before these other browsers became popular, we can imagine that Internet Explorer is probably one of the most popular browsers, even though today now it's called Edge, but it isn't. By most technologists, it's not a heavily used browser, right? But grandma, grandpa, they're probably clicking on the blue E to launch that's where the internet lives, is behind the blue E. Okay, so you still have a lot of people using this. So other browsers had to make themselves also compatible with those pages. Otherwise, you might have a huge set of websites that don't look right. All right, so HTML is kind of a loose representation of what is legal HTML code versus what is acceptable or what will be viewed correctly HTML code. Okay? XHTML would require completely accurate HTML. That means every opening tag has a corresponding closing tag. That's really the biggest thing. Is probably the biggest example with old school HTML, where if people were creating a list, either a numbered list or an unordered list, you have an opening UL tag and a closing UL tag for unordered list. And then in between, you have list items. And each of those list items is opening LI tag and then your list item. It was really common to do opening LI tag, list item, but never have a closing LI tag. And then the browser would just say, oh, you have another opening LI tag, so we'll assume you're starting a new list item. But technically, that's not accurate HTML. That opening LI tag should have a closing LI tag. Does that make sense? So they had an exception for that. XHTML would not allow for that. If you have an opening tag, there better be a closing tag associated with it. That's the way it works. All of them now. Yeah, I mean, the original problem, and this isn't necessarily to demonize Microsoft. You know, the original problem was Internet Explorer was the most popular browser because it was made by Microsoft. And a lot of people in the early days of the web, you know, people who were not technology people were making websites for their companies, their small businesses, whatever. And they were using a Microsoft product called Microsoft Front Page that allowed them to visually create a website. And Front Page, when they hit save, Front Page created HTML, an HTML representation of what they just designed. And what it created was not accurate HTML. It has happened to be HTML that worked in Internet Explorer. And then all future browsers, they had to make sure that all these sites that were created in Internet Explorer still worked in them. Okay, so this is it has more to do with just not necessarily knowing what they have and not following the rules. And instead, Microsoft just said, look, it's easier for us to produce this HTML. It might have been some junior developer. Front Page might have been just some, you know, project some people were dabbling in, and then it just turned into something that was fairly heavily used. That makes sense? So it really isn't, I think, substantially different than maybe the whole Y2K bug. You know, where, you know, when people were writing software in the in the 70s and 80s, and they, you know, stored a year as a 2-digit number rather than a 4-digit number, they didn't think about the consequences, right? The year 2000 is 20, 30 years off. Our software is not going to be running then. But then we hit the year 2000, and all of a sudden your programs can't differentiate between 1900 and 2000 because they're both year 00. Make sense? That's the Y2K bug. It's not necessarily an incompetence thing. It's just it's not a problem thing, right? You know, it's not necessarily dissimilar to like, this milk's only a week expired. It's probably fine. Probably is fine. A week expired. A year expired? Things get a little bit more sketch. So, yeah, in any case, a lot of times when humans solve problems, we don't necessarily, you know, we only think ahead so far for where it makes sense for us, right? It just so happened that computers ended up being a really big deal, and a lot of software that was correctly written years ago. It's like kind of the idea, if it's not broken, why fix it? So until it is broken, because tomorrow is the year 2000, and it's our software is going to die because now all the sorting is going to be wrong because it's not going to be able to differentiate between 1900 and 2000. All right, so this is just kind of a side effect of the power of technology. So, you know, HTML was a great forerunner for data representation languages. You know, somebody had to actually, it was originally created by some universities. I think I don't want to say this with full, I'm about 80% positive. UW-Madison, definitely University of Illinois, Urbana-Champaign. You had this collection of universities that were kind of the forerunners of the internet, and they were using HTML to transfer information between each other related to research and things like this. So in any case, you know, HTML was a great forerunner for this data representation type stuff. And then all of a sudden, as programming, as software became more and more prevalent, we said, hey, what if we want to share information between other kinds of programs, not just internet stuff? That's where XML came from. Make sense? All right. Now, when we look at something like this, one thing that pops into our mind is there's a lot of stuff here, right? Okay, now this is kind of a horrible example because there's a lot of JavaScript sitting in here, but let's just pretend this is a big wall of HTML. All right, lots and lots and lots and lots and lots of stuff on the screen, yet relatively speaking, not that much data, especially when you go and look at Google's page. This is a fairly simplified page, right? Even though Google has quite a bit of magic happening behind the scenes. All right, but the idea is that XML and XML-based languages, tag-based languages, tend to be fairly wasteful in terms of the amount of the file size relative to the actual amount of data you're storing. Does that make sense? So if you're storing a first name, a last name, and a birthday, let's say, you're going to need 1, 2, 3, 4, 5, 6, 7, 8. You're going to need 8 opening and closing tags to store 3 pieces of information. Make sense? There's a lot of fluff is the punchline. All right, so The more recent cool kid is this thing called JSON. And anybody know what JSON is? Now, if you've had 200 or 250 with me, you've seen this phrase before. It just has slipped out of the brain. Is that what's happened? Yeah, you've seen it before, right?
JavaScript one, right? The JavaScript object notation.
Yep. Does that come out of your head or come out of your notes?
Come out of the notes.
That's fine. At least it proves that I covered it. All right. All right. So this stands for JavaScript object notation. Now, why is it called that? Where do you think this came from? Script. From JavaScript. Yeah, it's actually an interesting programming thing as well. Most of us would assume that Java and JavaScript are the same. You know, they're at least second cousins or something like that. Not even related. Yeah, just happen to use a lot of the early. You know, this is kind of a technology type thing, right? You know, where we come up with like kind of catchy names for stuff like. You know, so when Sun Microsystems came out with Java, which JavaScript was not made by Sun Microsystems. JavaScript predates Java, you know, but when they came out with Java, then they had some other, like their complementary IDE, like we've used Eclipse in a lot of our classes. So that's become kind of the industry standard. But do you know what well, it's now Oracle, but you know what Sun Microsystems IDE, like kind of their competitor with Eclipse is called? It's called NetBeans. Get it? Like Java is like coffee, beans is like coffee beans. You get it? All right. So you had a whole lot of naming conventions that really had very little to do with technology and more to do with just they're catchy, right? So you know, we had a scripting language. Well, what's a scripting language? Well, you know, typically a scripting language is shorthand for saying it's an interpreted language. Okay, and a lot of times when we're talking about scripting languages relative to webby stuff, we're talking about languages that the web browser knows how to run. In the early days, we had two competitors. We had JavaScript and we had VBScript, Visual Basic Script, which was a Microsoft thing. So in the early days, Microsoft was very much a proponent of their VBScript, which their browser still supported. I'm going to call it 90% certain that they still support it. Nobody uses it anymore. Nobody writes it. But if you had some website left over from 30 years ago, it'd still be a thing. Probably not 30 years ago. It'd be 20. Web was kind of a thing in 93, probably. 94. Somewhere in that ballpark. I mean, it was a thing before that, but that's when it was a people used it thing. Before that, it was like universities, researcher, people used it thing. And all of you remember 1993 and 1994? It's kind of fresh in your mind. All right, so JavaScript object notation. This is actually how JavaScript accomplishes object-oriented programming. So JavaScript was not naturally an object-oriented language. So this kind of goes back in our connection between like C and C++. Well, C was a procedural language. C++ is an object-oriented language. What's the difference between them? Well, object-oriented language is like our telephone, hides all the wires, all that stuff. Well, so when we expanded JavaScript to support objects, we had to have some way of representing objects inside of JavaScript. Hence, JavaScript object notation. Make sense? Okay, and what's JavaScript object notation? It's a way of us kind of visualizing or us representing the information that goes into an object. Now, what's an object? If we think about objects, let's close our loop here. If you think about objects in any programming language, so many of you are currently doing stuff with Java, we're doing C# in here. The answer is the same regardless of those two languages. What's an object? An object is a collection of what three things? That's game object. I'm talking about programming in general right now.
Scale.
Now you're talking about, pretend like you've never seen Unity. Okay, none of the words involving Unity are going to be answers to this question. I'm talking about a plain Jane programming object and an object-oriented language. What are the three things that make an object? We have fields, we have constructors, and constructors, and we have methods. Those are the components of an object, right? Okay, what are fields? These are name value pairs that hold the data owned by this object. What are constructors used for? Yeah, creating instances of an object. And what are methods for? Doing things related to the object. So adds functionality. All right. Now, the functionality and stuff like that associated with an object, this is something that we're always going to represent inside of our the code anyways. But let's say that we want to represent, I mentioned a little bit ago, like a patient record. All right. So if we use an example here, and we're going to create an object in, pick your favorite language, C#, Java, Swift, doesn't matter. Object-oriented programming is object-oriented programming. So we're going to create a patient record. We'll keep this simple. Maybe the pieces of information we want to keep track of is maybe the first name, the last name, and the date of birth. Okay, very simple object, right? All right, so if we were to represent this guy in, this is going to be the same whether we're dealing with C# or Java. So let me just do it in Java for us, since we've written limited C# code in here, and the only C# code we've written has been stuff that's very related to Unity, right? Yeah, all of us are very familiar with Java stuff, so I'll just put it in Java, but I promise you'll have to make an extremely small number of changes for this to just compile as is in C#. Okay, these languages are extremely related. All right, so I'll just kind of create a real quick object that represents this information. So I might say public class patient record. And then inside here, let me drag this down a little bit. I would have a private string fname, private string lname, and private string DOB, date of birth, something like that. Then I might have a constructor for this guy. So public patient record takes in a string fname, a string lname, and a string date of birth. And then I would set this dot fname equal to fname. This dot lname equal to lname. And this dot dob equal to dob. Something along those lines. So is that a Java representation of an object, a class, that would allow us to hold information related to a patient record, and that information being the first name, the last name, and the date of birth? This is the code version of that guy, right? All right, so everybody sees that connection? All right, so if we are writing a piece of software that needs to work with patient records in terms of the objects that they are, well, now we can create, we can have an array of patient records. Or if you've had 300, we could have a linked list of patient records or a stack of patient records. So all sorts of things like that. And each of those patient records will have a first name, it'll have a last name, it'll have a date of birth, that kind of stuff, right? Now, let's take this a step further and let's think about how does a program work. So generally speaking, if you walk into your dentist's office, something like that, doctor's office, and they're going to have kind of an electronic medical record system of some type, right? That has patient records. They're keeping track of patient records, probably more than just first name, last name, date of birth, but simplified version, right? Where are those patients actually stored? I mean, when they get into the office in the morning, they double click on their icon and their electronic medical record software launches. Does that have all their patients hard coded into it? No, because what if they get a new patient that day? So they got to phone up the software maker to add the new patient in there, and then the software maker releases a patch to release a new version of the software that has this one additional patient involved? No, what happens when a new patient comes in and you add a patient? Where are you adding that patient? Server, probably a database somewhere, right? Okay, so we're going to say in this example, we're going to say patients are stored in a database. We're going to say on a server somewhere. This could be a server inside the office. Maybe more recently, this might be something in the cloud, right? In case there's a fire or something like that. This actually is a big field in computer science right now, dealing with healthcare. Okay, so as a normal software developer, we might say, oh, well, you can have your own little, how many of you have had the 430 class with Dr. Wall, the database class? None of you yet? Okay, probably next year, I'm guessing. Okay, but we've all heard of databasey stuff. Okay, we're storing stuff on some machine somewhere, and then we want our program to retrieve information from that somehow. All right, so maybe old school, we say, oh, we'll just create our own little server, our little database server. We're not Amazon. We have at any point in time 5 or 6 patients coming into the office or something. We don't need real heavy transactions per second performance, right? So you have your own little server. But the problem with having your own little server is now you have to maintain that machine. You're paying for the electricity for that machine. You have to make sure you back it up. The backups need to be stored somewhere. My dad was a dentist. So I remember as a kid, he would have, keep in mind these are very primitive kind of computing systems. So I wasn't that young, but regardless, he had a server in the office that held his database, and then every single night they ran a backup onto this tape thing, and then he would go and put that tape in the firebox in case the office burned down or something like that, so he didn't lose his patients, right? A funny story, the office did burn down years later, and that was an important piece of information stuck in that firebox. Okay, but in any case, that we might say that's a weakness of having your own server, right? If you're a dentist, you're in the business of dentistry, drilling teeth, making dentures, stuff like that. Okay, you're not a computer software, data scientist, backup person, right? That's not your skill set. Okay, so you maybe rather have that data handled by somebody else. Have somebody else handle all your backups, all that stuff, right? Okay, so today we think about these things as like cloud computing, right? Where our data is actually stored off-site somewhere. Does anybody know what the problem is with cloud computing as it relates to healthcare? This is a huge, huge, huge field right now. Many of you, when you get your CS degree and you go out and work in industry, might be working in something related to healthcare. It's a major boom right now. See, if we're just writing a normal plain Jane, like say a video game or something like that, where we're storing user accounts somewhere or whatever, we can just store them in a cloud database somewhere, no harm, no foul. But with healthcare, there's laws. It's called the big ones are called HIPAA. There's these things called HIPAA laws. So now there's all sorts of rules about what you're allowed to transmit over the internet and how it needs to be stored for confidentiality reason, right? You don't want people shouldn't be able to hack into your data and find out what all your medical stuff looks like and what diseases you've had and all this stuff, right? This is private information, and there's HIPAA laws about that. Okay, so now from a computer science perspective, we have to think about, well, how can we safely send information from our software to the cloud in such a way that's HIPAA compliant? That means we're representing it in such a way that HIPAA says this is fine. and it's encoded, and even if it was grabbed in the middle, somebody was able to retrieve the information while you're sending it, they wouldn't be able to actually distill information out of it related to the client. Make sense? So we might need to send the data in pieces and then have the server at the top kind of reassemble them. Maybe there's like weird codes and stuff like that. So maybe I send something about, your last dental appointment, but your name's not attached to it. It's just some random number or something like that. So fine, they find out that so-and-so had 3 cavities, but who had 3 cavities? Number 146 or something like that. That's who had 3 cavities. Who cares? We don't know if they're male. We don't know if they're female. We don't know where they live. Nothing. All right. So HIPAA talks about different ways of how do you transmit data, and similarly, how do you store data. So if somebody were to breach the system, they can't actually get real information about a person. They get information, but they have trouble connecting it to the actual person. Okay, so big field with cryptography for encrypting the data, as well as systems for transmitting the data. All right, so this whole data representation stuff, while on the surface might sound boring because it started off as HTML, is actually big bucks. Big bucks. Okay, so how does the program work? In our case here, our patients might be stored in a database somewhere. Okay, and we're not gonna deal with HIPAA compliance. We're just gonna assume we're good. Okay, we're flying under the radar. This is really actually the data, the patient records. We're just trying to sound really fancy. This is an old Blockbuster video store. Okay, we just store our things as patient records. All right, so we store our patients in a database somewhere. Then when we launch the application, it connects to the database so that we can look up patients as needed. Okay, so chances are it's not going to download the whole database into the local memory of the computer for running it. Instead, it's probably going to, as you type in, Mr. Lippman, you showed up today. Let's bring up your patient record. So, you type in, the last name, and they might ask you, what's your date of birth, to make sure we're dealing with the right record. And they say, okay, we got you. So then they bring it in, and that populates all the fields in the software that shows who this person is, right? But now when they did that, that data had to leave the database, had to get copied from the database into the software. It had to get transmitted somehow. So that means we had to represent that data in the database in such a way. Well, how it's represented in the database is unimportant in this scheme of things. How it's represented in our program is kind of like this, right? So ultimately, we need to get our data from the database into this format so we can create objects associated with it and work with it. So that means there's this path in the middle that needs to go from when we request the patient associated with Mike Lippman in the database. They need to send that information into the software such that the software can then parse out that information into an object. All right. So one way that can be done is with an XML record, or we can do it with JSON. We're representing that information into our program. Our program then parses that out into an actual object and then populates the different screens in the app. That makes sense? That's kind of the cadence of a piece of software. That's how software works today. All right. So when we retrieve a patient from the DB, it is serialized in some way. Okay, we talked about serializing a few minutes ago. That's going to turn it into a data representation language. Sent to the running program, which deserializes it and turns it into objects. Make sense? So that's how software works. Data stored one place. Hey, this is actually an example of MVC, right? It's a good idea to have your interface in one place, your logic in another place, and here's that third piece, your data in another place. Okay, the model is your data. View is your interface, controller is your logic. Okay, so we're going to store our model, store our data in the database, but we do need to get it into our program somehow. How do we do that? Well, we have to have some language that we can use for talking to our database. Anybody know what the popular language is for talking to a database? I think you've all heard it before. SQL. Seen those letters next to each other before? You had to have seen SQL at some point. Not learned it, just seen it.
On the internet?
Anywhere. You've heard of MySQL? The database software? Killing me. Get out of your comic books and anime. So SQL is structured query language. Okay, so this is a language that allows us to ask a database for information, and then it retrieves it for us. So I can say, give me all patients whose first name is Mike, whose last name is Littman, and whose date of birth is whatever. All right, make sense? And then it'll give me a list of patients, hopefully in this case just one, but that will give me, retrieve that one record from the database. Otherwise, databases lose performance. This is more of a 430, CSC 430 topic, or how databases actually work. But from our perspective, we have to have some way of asking our database for information. Give me the records associated with this information. All right, and that one example of how we do that is through something called SQL. All right. Ultimately, that data then gets serialized, gets sent to the program, which gets deserialized into objects that now, as a programmer, we can work with. Make sense? All right. So what we're interested in this, so are there any questions about this whole process? So this kind of started off as a data representation language lecture, right? Okay. And we want to see, so do we all recognize that this is something that is well beyond game programming, right? This is something with how software in general works. This is related to MVC. Store our data someplace, logic someplace else, interface someplace else. All right. Now, how are we going to connect it to what we've been doing in here? Well, we might want to design a bunch of rooms or something like this. I think I mentioned we're going to kind of create the department here, right? Okay. But we might want to represent the dimensions of those rooms, the number of rooms, all this stuff. We might want to represent that in a data representation language. Then when our program launches, it reads in that serialized code, it deserializes it, and turns it into game objects in our system of the correct size and correct location. Does that make sense? So we can actually build our department textually. You can say, okay, well, we have this one room. Its location is at this XY coordinate, and it's a 23-foot by 17-foot room or something like that. You represent all that in some data representation language, and then your code can read that in and build out the environment. And if you notice, oh, well, this room's a little bit too big, you go back and you tweak the data representational language a little bit, then you relaunch it, and now it should build a little bit smaller room for that particular place. Okay. So this is going to go back to this JSON thing. So I mentioned a little bit ago that one of the weaknesses of XML, not that it's bad, not that it's even a horrible problem, because our internet's fast today, relatively speaking. Textual data is not that big. I mean, if you were to transfer is it unreasonable to transfer a 1 megabyte file today? That's not an unreasonable thing. We would consider that would transfer pretty quick over most internet today, right? 1 megabyte. That's a lot of XML. Okay. A lot of XML can be represented in 1 megabyte because we're not storing any images. We're not storing a lot of that data. All we're storing is pieces of information. First name, last name, address, stuff like that.
So I mean, how big should your storage be in the smallest server by
Depends what you're storing.
Yeah.
I mean, if we just use our little patient record thing here, And we think about it from an XML perspective. Let's give ourselves an example of an XML representation of our patient record. Dump this guy. All right, so we're going to say we might have an opening patient and a closing patient tag. And inside this, we have a F name, maybe Mike. We have an L name, Littman. We have a DOB. Let's do 1/27, 1998. Does that give me drinking age? 1997? Yeah, I'm good. /DOB. All right. So might this be a serialized version of a patient record? All right. How much data does this take? Well, so as they say in one of the questions in the Big Bang Theory one episode is like, is that a rhetorical question or would you like to do the math? I'd like to do the math. How much data does this actually take to represent a single patient record? How are characters stored in modern computing? You all know this. Unsigned 16-bit value, right? So each of these individual characters belongs in the Unicode character set. So it's a 16-bit unsigned value. So what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79. So as an example, 79, as your data becomes bigger or smaller, in this case, if my name is longer or shorter, stuff like that, it's going to wiggle by a little bit. But let's just say in this particular example, we have 79 characters. Okay, so we have 79 characters. Each of those characters is 16 bits big, right? So that means that 1,264 bits make up a single record. Right? All right. Now we talked about a megabyte before. How many bits are in 1 megabyte? Okay, so let's I'm just going to copy this real quick. So 1264. All right, so we're going to say 1 times 1024 gets us to kilobytes times 1024 gets us to bytes times 8 gets us to bits. So that's the number of bits in 1 megabyte. Now I'm going to divide that by, what was my number? 1264? So 6,636 patient records and change. Patient records can be stored in that amount of data. Okay. Is that a lot of, how many patients do you think an average dental office has?
100.
Okay, probably less than that. Probably less than that. Now, this is only, so for transferring 1 megabyte of data, which we said wasn't that big of a deal, right? That means that I can download the entire database in 1 megabyte of data. If we assume that we have 6,636 patients, I can get the entire database. Now, really, since we're using SQL, we're just saying, hey, I want one record. Give me one record. And one record we said was 1264 bits, right? So 1264 bits divided by 8 gets me to bytes. Divided by 1024 gets me to kilobytes. Divided by 1024 gets me to megabytes. How long does it take to download 0.00015 megabytes? Yeah, very little time, right? Almost instantly. So that's how big a single patient record would be as we serialize it, send it over the network, and have it deserialized on the machine, in our case, in the game. Make sense? Okay. So we're dealing with very little data. That's our example of MVC as it relates to data. Data stored someplace else. I need to get it into here. How do we do it? We agree upon a communication language. In this case, maybe it's XML. So I just chose XML here, right? Separately, we can use JSON. So now if we look at the JSON representation of this, this is our XML patient record. So I'm going to create another guy here. I'll do this one. JSON patient record. We'll create some text. So we're going to create the same data, but in JSON format instead of XML. So we're going to have an opening and closing curly brace. We're going to have fname : Mike, comma, lname : Littman, comma, dob : what would I say, 1/27/1997? Is that what the thing was? All right. So that is the same. That's the that's the JSON representation of that same patient record. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. So almost half the size, right? 45 compared to 79. So much less fluff. So this is more efficient, even though we said XML wasn't really a problem. Okay, so if you have current data sources that are out there that are sending information in XML rather than JSON between two programs, they're not necessarily highly motivated to go and update it to do it in JSON, even though converting it isn't that huge of a deal. Why is that? Well, because it's not really a problem. You know, we can download a single record pretty quickly. You'd only really be, in fact, generally speaking, the biggest reason why current places convert to JSON has to do with something called a RESTful API. How many of you have seen this phrase next to each other before? REST API. Okay. So, and again, this stuff, even though it's directly related to game programming, it's directly related to any software development. So when I say third-party APIs, what we're really talking about here is we're talking about other companies' data being made available to us through a programming interface. Okay, that's what a third-party API is. So, for example, if we are writing a mobile app and we want to bring Google Maps into our mobile app, right? Okay, would it be in our best interest to reinvent the whole navigation mapping process, or does Google do a pretty decent job of that? Okay. Google does a pretty decent job of that. So if we want to have that capability inside of our application, it would be in our best interest to go ahead and talk to Google Maps through their advertised API, through their public API. And in that situation, they will ask them, give me these series of instructions for X, Y, or Z, whatever, and then it will serialize that data, send it to us. We will then deserialize it and use that data inside of our program. Maybe we're trying to get the distance between Memphis and Chicago, something like that, right? So one of Google Maps APIs probably has a way for you to request information about the trip between 2 points. You can give it Chicago, you can give it Memphis. It'll tell you maybe the list of roads you'll take, the amount of time you're on those roads, and the total distance of the trip, something like that. And it's going to take that data and it's going to represent it probably in JSON. Okay, so it's going to serialize it in some way, send it to you so that you can deserialize it and use it inside your program. All right, so that's the point of a third-party API. All right, so continuing down this path, are we all convinced that it might be helpful for us to talk to other data sources with our applications? Okay, it could be PayPal. Maybe we want to handle payments inside of our app. And rather than us inventing a relationship with a bank, why don't we just go ahead and let PayPal get their 3% or whatever of all the transactions and just use them for doing it all? Then we don't have to worry about credit cards. We don't have to worry about security. We don't have to worry about any of that. They give us the conduit for doing it through their API. All right, so we're all good on that. We want it. Okay, so now we have to have a way of accessing it. Well, historically, talking to third-party APIs like this would have been a fairly proprietary type of endeavor. Okay, meaning that if you wanted to talk to Google Maps, you had to learn the Google Maps way of talking to them and getting their information. If you wanted to talk to PayPal, you had to learn the PayPal way of doing this stuff. Okay, well, over time, we've moved towards this standard. Okay, and that standard happened to be called REST. All right, now, how many of you have heard of, let's do this in a separate, something called HTTP? Seen that before? Seen that before? That has an S on it. That's secure HTTP, but still. So, how many of you never actually noticed it up there? It's kind of one of those things that's, just not important to us, right? Do you know what it is? What does this thing right here say? When I say HTTP : / what am I saying here? I don't care what it stands for. I mean, I'll tell you what it stands for in a minute, but I care more about what we're actually doing there. Did they just decide we're going to write some extra characters because it's fun? So I'll just put some more stuff in there. Okay, so we're kind of requesting a protocol. We're saying, I want to send this string, www.icloud.com/ blah, 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 blah. I want to send that over the internet using the HTTP protocol. Now, the HTTP protocol, this guy stands for hypertext. Transport protocol. So HT, hypertext transport protocol. Where have we seen that phrase hypertext before? What is hypertext? What is this guy? We've seen it in the last 20 minutes. This is a really interesting lecture. You should go back and re-listen to this lecture. This is like gluing all sorts of pieces, how software connects. What does HTML stand for? Hypertext Markup Language. So what do you think Hypertext Transport Protocol is for? Send HTML. Okay. How old do you think this guy is? How long has HTML been around? Since the internet, beginning of the internet. So did we need a way of transporting hypertext in the early days of the internet? Okay, so HTTP kind of been around for a while. So do you think it's probably been stress tested and proven to be, you know, let's call it relatively bug-free and stuff like that? Okay, so this guy, we can just generically say used, well, I'm going to actually say it this way. Historically used for sending websites over the internet. That's what it was for. All right. Now, Hypertext Transport Protocol actually had 4 functions built into it. Very easy functions. So we had something called put, post, delete. What's the last one? Update. Okay, put, post, delete, and update. All right, so these are the functions that are part of HTTP. All right. Update doesn't sound right to me. Oh, it's not. It's not. Get. Post is my update. All right. So actually, put is my update. Post is create new. Get gets an existing thing. Delete deletes an existing thing. Okay. So we had 4 functions. These 4 functions are the way that what the HTTP protocol supported. Okay. But the reality is, if we're just sending websites over the internet, the most generic way of doing that was with a get. This is just plain text, send it over the internet, blah, blah, blah. The other way of doing it would have, well, so that gets your data. So if I say google.com, get me index.html, send me that HTML document. That's just a get request. So we can probably just say that 90% of all requests that happen on the internet, probably higher than that, 98% of all requests that happen on the internet are just gets. And then every now and then, if you have to like submit a web form or something like that, you're going to be using a post. All right, to kind of like, you know, put your username, put your password in. We're going to put that together in a little package and send it out over the internet for somebody else to catch and make sure you're authenticated or whatever. Okay, but generally speaking, we only use these 2. So we're only using half of the functionality of HTTP, because HTTP was originally created to be more of a generic solution, even though we only leveraged it for gets and posts for the last 30 years. Okay, but now with REST APIs, we are going to leverage the HTTP protocol to accomplish something called CRUD. Create, retrieve, update, delete. So now, if you were to consider what you might want to do with PayPal, or you might want to do with Google Maps, okay? With PayPal, might you want to create a new transaction? Sure. Might you want to retrieve information about an existing transaction? Sure. Might you want to update an existing transaction? Yep. Might you want to delete an existing transaction or delete a transaction that's being processed? Sure. Now, if you consider that, can anything that you might want to do with PayPal not be represented in terms of one of those 4 functions? You might want to create different kinds of things. Maybe you want to create a transaction, a one-time transaction. Maybe you want to create a once-a-month type of thing. Maybe you want to send money to somebody. Maybe you want to get money from somebody. Whatever it is. Okay, you have different types of transactions you might want to create, but you're still always creating. So could we generically say that every single thing you might ever want to do talking to a third-party API could be accomplished in these four generic ways? Is that a fair enough statement? Well, the people who are creating APIs decided, yeah, that makes a lot of sense. We can represent all the ways you might want to talk to our API in these four functions. And you know what? It just so happens that HTTP, this thing that's been around forever and ever and ever, has those exact four functions built into it. It's already been stress tested, been used for years and years and years and years and years. It does exactly what we need it to do, no more, no less. Why shouldn't we just use something that's been laying there, mostly dormant, for 30 years to accomplish stuff that we're doing today? Makes a lot of sense, doesn't it? That's what a REST API is. A REST API, sometimes you'll see it written as RESTful APIs because it sounds cooler. Just say RESTful. Okay, that's all the whole technology buzzword type stuff. Okay, it sounds cooler. So these things have been around for a long, long, long time. Well, HTTP has. Now we've just decided, well, why don't we make all third-party APIs leverage HTTP, but we'll call it something new. We'll call it a REST API, which implies that it's using HTTP because that makes life easier. Make sense? Questions, comments, concerns, bribes? All right, remember today's student, faculty, staff Bible study, God and Grub. You can go to the cafeteria, sign in, get a free lunch, take it down to the terrace room. We will pick up where we left off on Thursday. Remember, you have another assignment due on Thursday, so keep up with the assignments that are already posted on Blackboard. Sound good? All right, I'll see everybody on Thursday.